I want to tell you about what we have learned about transmission of the SARS-CoV virus. And there's been a lot of debate early on about the mechanism for that. And it was all wrong. And it really exacerbated the problem. So I want to just quickly go through this. But before I talk about that, I'd say that, well, my pre-pandemic focus has been on a different type of photonics, doing time-resolved crystallography using lasers to excite things and X-ray pulses to monitor structural changes in proteins on timescales from 100 picoseconds to nearly a second. And we could use this to study near atomic resolution structural changes in real time. And with that background, all of a sudden, we weren't able to do that anymore. I was preparing for a run to go to Chicago to continue some of this work, and early last year. And because of this pandemic, and here's a slide that shows where we are currently at. This is why we're actually seeing each other virtually through Zoom rather than in person. It'd be much nicer to visit Duke in person, I'm sure. How did we get to where we are now? Well, here's a graph showing some representative countries and how things have been handled during this pandemic. And this is a linear scale showing most places have suffered two phases of this growth. And in this case, it's a cumulative deaths per million. You see, US is a superpower, and we're a leader in many areas, and we're a pretty good leader in deaths per million people as well. Where it started, and in these Southeast Asian countries, it's far, far lower. They've been able to manage this pandemic much better. Now, this is a linear scale. It's helpful to look at a log scale to see how things actually started, because now you can see the details where it started with China, and then it went up, and then it basically flattened. And one of the Taiwan is very close to China. They were early impacted, and they flattened the curve. South Korea is very close. They flattened the curve. Japan, you see they flattened the curve and didn't suffer nearly as much as the rest of the country. And why is that, as we'll say? Now, I highlight here Saturday, March 21. So that day is significant for me, and here's why. That week, I was busy preparing for upcoming beam time, and at AdBax, a colleague of mine down the hall came to me, and we were of course watching what's going on with the pandemic and wondering, with this stuff happening in Asia, in particular Italy, what is the impact here in the US? Is the US going to shut down? There's talk about that, and what impact will that have on our research? And he says, the CDC, they're saying that this COVID is spread through fomites, and then through respiratory droplets by coughing and sneezing. But his wife is a linguist and understood that we actually generate a lot of droplets when we're talking to each other. Speech droplets. I hadn't heard of these things before. And so because of my background with lasers, photonics, he was asking if might there be a way one could visualize these droplets as they come out of our mouth, and then so we can get that information out there so people can mask up and curb this transmission of this terrible virus. And I said, yeah, I think we can probably do something like that, but I'm busy right now. Well, that Friday, the day before, March 20, came around, and I got an email saying that no, my beam time wasn't happening. And so then I thought, okay. And then I started talking about shutting down. So there's a window of opportunity to get something done. So Saturday, March 21, I got into the lab very early. Actually, on Friday, I gathered up some optics to see if I had everything I needed, and then started laying things out, cleared out a portion of my laser table, and started putting some optics on there to create a laser light sheet, shoot it through a box. There you can see the laser light sheet passing through my lab. Now I have a laser lab, and I have HEPA filters sitting up on top of a support structure that goes around my laser tables, and then curtains I pull around them. So I can have a pretty clean environment that's just sitting there ready to use, and seemed like ideally suited for doing these kind of measurements. And so that Saturday morning, I set it up. I got the light sheet going in there. Okay, now I need somebody else. And it just turns out our machinist was next door trying to finish up on some things. This is real dedication when a machinist comes in on a Saturday at the NIH. So I grabbed him and I said, I need a set of eyes. I want to find out if I talk through this light sheet, can you see something happen? And indeed, he could see something happen. So then I picked up the phone and called a postdoc in my research group, Valentin Stadnitsky, and then AdBax, and they came in, and then we started experimenting with what kind of sounds generate how many particles, and yeah, they lit up like fireworks. And we tried some very simple things. Just take a paper towel and stretch it across a face and then try to talk through that. And yeah, you can talk through that, but it basically does a pretty good job of capturing that. You see very few particles coming out. And, you know, they talk about super spreaders. Well, I can generate quite a few droplets, but so can everybody else. So this is something that's generally going on when we're talking to each other. We have these otherwise invisible particles spewing out of our mouth in abundance. And then if we breathe them from a neighbor who's infected, we have the risk of getting that infection ourselves. So the aim was to get the word out as quickly as possible because the CDC didn't have the right story on this. WHO didn't have the right story on this. And this seems to be the most logical way for this rapid spread that we were observing in other parts of the world. So we stitched together a YouTube video. Now, we aren't authorized to speak on behalf of the NIH. We're just some basic scientists here. And so we published this or posted this YouTube video anonymously. But we wanted to have some credibility. So the former director of NIH, Harold Varmus, was actually a rowing buddy with AdBax. And he contacted Harold and asked, would you be willing to record something in support of this conclusion that, you know, masking up is going to be the best way to help curb the spread of this terrible virus? And so he gratefully sent us a video clip from New York, where he was at the time, and we got that stitched together. So on March 21, we set up in my lab some laser optics. March 24, nobody ever had done anything like this, uploaded a YouTube video, thanks to Valentin Stadnitsky, who figured out how to do all of that. Then we got to work to see, well, what kind of speech actually generates droplets. And so, you know, we basically took turns reading the Gettysburg Address into this, and then quickly learned that there's certain sounds that come out of your mouth that are pretty productive. And ironically, stay healthy is one of those combinations. And so here basically said, stay healthy inside this box 3 times in succession. And that first blip you see in particle counts is from stay. And that second one is much bigger. It comes from healthy. Well, what's happening there? When you make the TH sound, where you put your tongue basically narrows down the cavity, and you can get a high velocity of air coming through, and then you're able to generate far more droplets. And so, yeah, we could generate a large number of droplets. We got that paper submitted by March 29, you know, just a little over a week of setting this thing up in the first place. And then, although we complained about it being slow to get through the refereeing process, it was published online by April 15. Then, once you have these droplets in the air, what is their fate? So instead of that Amazon box that just painted the inside of it, the outset to get the initial experiments off the ground, then fabricated a box with some fiber board, some black fiber board, and then made it a little bit fancier. There's the slits going in. You see the light coming through. We just sprinkled some droplets in there to get it to light up. There's a speaker port on the backside. Installed a little fan, a computer fan in there. And the idea was once you speak in there, when the box is closed, then we can stir things up and try to get the droplets uniformly distributed in the box, and then shut off the fan and then watch them fall. And then there's a purge port on the top. This is sitting immediately below a HEPA filter. So we can open up that purge port and kind of blow out all the particles, get it clean before we start the experiment. And then it had temperature sensors above and below just to make sure, you know, what kind of gradients in temperature do we have if we have convection currents, and stir it up. And then when we close the box, just put a little iPhone on the side, and you actually see this green slab going across. That's the light sheet from the Rayleigh scattering inside the box. And then that hole, that white hole, that's actually light leaking through from the backside with the lights on. Of course, we shut the lights off to do these experiments. And then after filling the box, saying, stay healthy a number of times, and then stirring up the fan, shutting it off, and then watching the particles fall over time, we found that the brightest ones fell more quickly, maybe about an 8-minute 1/e time, and the weaker ones fell a little bit more slowly, about 14 minutes in time. But what does that tell us? That of these droplets that are clearly evident from the scattering experiments, they linger around in the air for many, many minutes. And in that amount of time, of course, the convection currents or the room air currents can stir things up. Is 6 feet safe? You can't say that 6 feet is safe, because these particles are roaming around. Then here's kind of a timeline of this process, because we were out to try to get this information out to the public as quickly as possible, so hopefully better policy decisions could be made. So just to review, on March 21, set up the laser. On March 24, we uploaded a YouTube video. And then March 29, we submitted a paper to the New England Journal of Medicine. And then that paper manuscript was circulating at the NIH and the CDC. And that led to a phone call between Ad Bax and Matt Pottinger, who at the time was a Deputy National Security Advisor to the United States. That was March 31. And they discussed the risks of unmasked speech. Well, Matt Pottinger tried to call me twice that day as well. I didn't actually speak with him. Somehow the White House switchboard came off as Egypt. And I wasn't going to answer a phone call from Egypt because I don't know anybody who would be calling me from Egypt. Anyway, but the communication did happen. And then later on that week, on April 4, CDC revised its guidance. And at that time, they identified speaking as a source of transmission. Before, they were talking about coughing and sneezing, but now they said speaking was a source of transmission. And then they recommended face coverings, which they had not done before. But guess what? How did they frame this? Wash your hands, don't touch your face, and wear a mask. It should have been in reverse order, because the speaking and the mask wearing is going to be far more effective than making sure your hands are clean. Then we submitted soon after that the paper that discusses how long these particles survive in the air, how long they linger in the air. That was April 10. And then on April 21, there was tentatively scheduled an interview. CNN wanted to have an interview with the scientists from the NIH, and the NIH volunteered me. So they were prepping me for this interview. And then just the night before, the day before, scheduled interview took place, guess what? We got informed by the Office of the Vice President that that interview was not allowed. They want to control the messaging. And so CNN ended up getting some video clips, which we could do, so we could supply them. And they did do a story on this, but we weren't permitted to actually talk about it. So the wearing of masks was kind of clear from this work is going to be a crucial part of trying to mitigate the impact of this pandemic. But as we all know, this got highly politicized, especially in America. So as a result of this work, we were invited to write a review article to discuss this transmission, modes of transmission, and try to make a convincing case where it is coming from. And so this review article was just recently accepted just a week ago by the Journal of Internal Medicine. And there we discuss, what kind of droplets are generated, something about their size, and what basically is driving the transmission of this disease. And it's really kind of interesting. I'm a physical chemist by training. I knew nothing about this stuff, but it was kind of fascinating learning. Our respiratory system is really remarkable. An average adult respires 10,000 liters of air per day. And they go through the trachea, down the throat through the trachea, and then they split. And you have splitting like branches of a tree. And these airways split 23 times before they get to the alveolar sacs. So if I take 2 to the 23, well, that's over 8 million. We've got a lot of those sacs. That's where the oxygen and CO2 exchange takes place. Interestingly, the first 5 branches that take place preserve the total cross-sectional area of the airways, which means that whatever velocity of air is going through the trachea is preserved through the first 5 branchings. After that, when they continue to branch, the diameter shrinks down more slowly. So that means the airflow slows down as you go deeper and deeper into the lungs. The diameters of the last branches are about 0.4 millimeters. Now, they can't get too small because otherwise, by surface tension, given water, it will want to plug those channels, just like capillary action. But we have surfactant in the mucus in our lungs to help minimize that. Now, when you then breathe, every breath basically cascades that volume layer. It's of the order of a liter per breath that you're going to take. And that's going to be spread over a surface area of about 50 to 100 square meters. Now, they talked about, not only face masks, but maybe you should wear a face shield to cover your eyes, because they say don't touch your eyes. So there's that idea out there. My mother lives in an assisted living place, and they insisted that visitors not only wear masks, but also a face shield to protect eyes, I guess. Now, what is a square area of an eye? Well, 2 times 10 to the minus 4 square meters. You compare that to the area of the lungs. It's about 6 orders of magnitude smaller surface area presented. So wearing a face shield to try to protect yourself against droplets, every breath you take, you're spreading out the droplets that are in the air near where you're breathing over a huge surface area. So airborne transmission surely is got to be significant. Now, what we do have going for us in our lungs is in these small tubes, in the respiratory tract, we have cilia that lines those airways. And those cilia are about 7 microns long. They beat at 10 to 20 hertz. And that causes the mucus in the lining to move upward, up the trachea, into the throat. And then we basically swallow or spit that stuff out. And that moves at a rate of about 1 millimeter per minute. So we cleanse our lungs at a reasonable time frame. So if you get a droplet landing inside your lung, it will be eventually swept out, but it could diffuse through the mucus and get to a cell and cause an infection before that happens. And so that's what we're worried about. How do these droplets get generated? Well, it's a very simple procedure, simple thing. Our lips are wetted, our teeth are wet, our tongue is wet. When we open and close our mouth, whenever these 2 wet surfaces come in contact to each other, when they separate, you get a film. And that film can be in the form of ribbons, a long ribbon, or little strands. But when we're exhaling as we speak, that basically pushes it, it gets thin, it bursts, and then the water, because of its surface tension, forms a bunch of droplets and they come out. So you can get breakage here from vocal folds, and then here from parting lips. Or if you cough or sneeze deeper in the lungs, then you can have very high velocities where you can get turbulent airflow. And then you can cause things to kind of rip free from that mucus. And those gives rise to the larger drops. Now, once they're emitted, what is their fate? Well, we need to think about terminal velocity. Very simple equation. A sphere falling through a fluid, let's just use a sphere because these are spherical when they come out, falls at a constant velocity when the gravitational force acting on it equals the resistance. And the resistance, frictional force here, basically, according to Stokes' law, is just proportional to viscosity. So their terminal velocity times the viscosity times some other terms, basically we get that matching. So now with a sphere, we can do a substitution here and then get and convert from mass. It's kind of, you have mass on one side, you have radius on the other side. Let's get this unified and have the mass where we recognize that the density of an object times its volume is equal to its mass. And then we get an equation that we simplify and we find that the terminal velocity goes as, now I rewrote it instead of R, radius, as D, diameter, because most of the literature on this is published in diameter. So the terminal velocity is proportional to the diameter squared. And so that means that if a particle that comes out 10 times smaller, it takes 100 times longer to fall. So let's get a representation. A 10 micron particle, get a benchmark, falls at a rate of 2.7 millimeters per second. So that's a fairly slow falling rate. A 1 micron particle will fall 100 times slower than that. So they linger in the air for quite a while. Now, what is a 10 micron particle? We've all seen a fog. And then we're out in the fog, those are nominally 10 microns. I didn't actually realize there's different characterizations of fog, maritime, cumulus, continental, but they're all kind of bunched up around the 10 micron. You have components around the 10 micron size. Now, when they come out of our mouth, they come out wet. Most of the droplet is water, 95% nominally. So when you have 95% evaporating away, the droplets are very small, high surface area to volume ratio, so they can evaporate rather quickly. And when they evaporate, then they're left behind the nucleus, the dry nucleus. And so they shrink, and they'll shrink by roughly a factor of 3. And that basically goes according to the cube root of their volume. This was recognized a long time ago by Wells, 1934, who illustrated this, that if you have things falling, how long do they fall before they evaporate? Small droplets, they don't fall very long before they evaporate. Big droplets can fall longer before they evaporate. And once you get above a certain size, above 100 microns, then these things make it to the ground without evaporating. So those guys, while they're big and can have a higher probability of carrying a virus, they fall to the ground and are much less likely to be inhaled. Now, Roland Netz tried to do a little bit more refinement of this study and then came up with what he calls a sedimentation time, tau sed. And he tries to take into account the relative humidity in these calculations and also on the amount of salt and other constituents in there that can slow the evaporation rate. So we use his equations to try to come up with what we call the airborne infectious lifetime. So we use his sedimentation time, and there's a relative humidity dependence of that. But then we add in there like the virus lifetime. It'll survive in the air of the order of an hour, but that limits how long it can remain infectious. So these very small particles can linger in the air for days, actually. But if they don't remain infectious beyond an hour, we don't have to worry about them beyond that time. And then there's the air exchange, tau x. How rapidly do we exchange the air? So the solid lines are with no air exchange. The dashed lines are with air exchange. And you can see the red curves is with a low relative humidity. The blue curves is with a high relative humidity. With a high relative humidity, the effective airborne infectious lifetime is decreased. But now this is a function of particle size. Now, what really matters is what is the volume that they contain, the relative volume that's emitted. And so we have a curve here that says the relative volume fraction for the different size particles. When you're breathing, they're all very small particles, as just pointed out. And that's well represented by a log normal distribution. When you speak or cough, it's a much more complex distribution. Basically, multiple log normals give rise to that. But now, what is the relative infectivity of these particles? Big particles, they have a higher probability of having a virus in them, but they fall to the ground more quickly, so they're less likely to be breathed. So if you take a product of these two curves, A and B, then we get what we see in C. So this is where it's really important to understand this. We see the relative infectivity is highest for these particles at around 80 micron. And this is the initial hydrated diameter. They shrink by a factor of 3 roughly when they dry out. So that would correspond to something like 20, 25 microns. Those are, they start out at 80 and they shrink to about 20, 25 microns. But those still fall reasonably slowly in the air, so as other people nearby can breathe them. Now, how much does relative humidity change? Well, when you raise the humidity, well, the airborne lifetime or the relative infectivity can be cut roughly in half. When you increase the air ventilation, it improves it, but not by a whole lot. But when you go to very small particles, that's where the air ventilation, as we heard, can make a very big difference. Because those guys linger in the air for a long time, but by having airflow, air circulation, room replacement, you can get that down to a much lower level. Now, this shaded area, this is a size particles that, if exhaled, can end up deep in a person's lungs. So COVID basically is kind of a tale of two diseases. If you get it deep in your lungs, you have a hard time. So what we want to do is minimize the number of droplets that go out there. And so the idea of masking, if you don't have a mask, you generate a lot of droplets, they spread far and wide. If both the person emitting them and then the person breathing has a mask, then you can reduce that probability of transmission greatly. This has been studied in much greater detail by Warren and his other collaborators, and Martin Fisher is going to be talking about that in a moment. And I think I have to conclude here. The CDC has now very recently updated its recommendations, and it says COVID is spread 3 main ways. And now what do they put number 1? Breathing in air when close to an infected person who's exhaling small droplets and particles. They got it right, and they moved that up to number 1. But guess what? They still say cough or sneeze, and they don't say, well, wash your hands, don't touch your face. And now we're working on a system to better characterize the broad distribution of droplets that are emitted. And so we understand their particle count and their volume. And so this is something that's built and operating in my lab. And this is some data that's actually collecting even as I'm speaking. Here's the part of the curve that's generated up till now, where we use a tower like it's like a chromatography column. So we introduce the particles in the top, let them fall. We know very good that, well, the physics of falling, the terminal velocities. And so when I recast that in terms of the size, here at 10 microns, it takes about 4 minutes to fall down. A 3 micron particle, about 48 minutes. A 1 micron particle, about 7 hours. It hasn't been quite 7 hours since I started that. And this is just characterizing some particles that were injected from a nebulizer just to get some benchmarks on this. We have some real heroes here. These
Bill,
two
I have
guys,
to ask you to wrap up.
Okay. I'll just say our vaccines, that's the ticket for getting out of this pandemic. And I think most of the people I know have been vaccinated. And I guess I'll just stop there and say I have to acknowledge Ad Bax, who coaxed me into getting involved with this. Valentina, a postdoc on my group, who did heroic work in getting this stuff going and work with us. And our machinist, of course, who has been helping out making all the stuff that we're doing. And with that, here's a final thought. These caterpillars are trying to cross a hot tarmac. And the ones in the bottom are crawling at their normal speed. The ones that crawl over the top are crawling at their normal speed, but they're going twice as fast. The average speed is 1.5 times the normal crawling rate. They spend only 2/3 of their time on the hot tarmac. Cooperation. These little bugs with a tiny brain figured out how to get to the other side more safely. It's pretty embarrassing how we've seen a lot of studies with optogenetics about the brain. With the brain capacity we have, why couldn't we do a better job of addressing this pandemic and not politicizing this? And with that, I'm done. Thank you for your attention.